Cellulose and starches come from renewable resources, are lightweight, biodegradable, and could improve the various applications they are used for. Both materials have contributed to a large portion of industry today, with cellulose being the most abundant renewable polymer resource and starch being the most common carbohydrate in human diets. There are ample resources and endless possibilities for advancements that could help ease the food, biofuel, and environmental trilemma. Cellulosic materials can be found in the cell walls of plants, wood, and in cotton linter. Cotton linter is found right around the seeds, while the rest of the cotton is used for clothing and fabrics. There are a variety of desirable qualities found in cellulose. Cellulose is a renewable and biodegradable resource that is lightweight, tough, sustainable, and has a natural feel to it. Even nanocellulose has advantages of high surface area, unique morphology, low density, good mechanical properties, and is widely compatible. This allows for easier reactions to be done at a quicker and cheaper rate. Derived from the glucose monomer, there are many derivatives to cellulose structures. Some of these examples include cellulose acetate butyrate, cellulose propionate, and ethyl cellulose. Each derivative presents different qualities and characteristics that can be beneficial in specific situations. There are many applications of cellulose depending on the derivative and scale size being used. Most cellulose are used for fibers and textiles because of their high absorbency, breathability, softness, and environmental awareness. Cellulose are diverse enough that they can also be used for tougher applications like spectacle frames, combs, and toys. Cellulose can also be added to other materials to act as a stabilizer, binder, and a thickener. The nanoscale version of cellulose can have many applications as well. Nanocellulose can be used for filtration, packaging, implants, hydrogels, paints and coatings, paper, and electronic sensors. Starches are found in potatoes, rice, corn, and wheat. The seeds and tubers that contain starches are crushed and grinded to gather the starch. The starch gathered is a white, soft, and tasteless powder. It is a low-cost, lightweight, and biodegradable material that is versatile in uses and can be added to other materials for functionality. Starches are mostly found in foods, but it can also be found in corrugated paperboard, paper bags, and boxes. Starches can be used in the textile industry to add extra strength to threads during fabric weaving. When combined with other materials, it can act as a thickener, water binder, emulsion stabilizer, and a gelling agent. An encouraging and newly emerging idea is to convert cellulose to starch to help reduce the environmental stress of using agricultural land. The annual resource of cellulosic materials is almost 40 times greater than the starch produced by crops cultivated for food. Additionally, cellulosic plants can grow on lower quality land and require fewer inputs like water, pesticides, and fertilizers. This transformation would increase efficiency on marginal land use to produce the biomass required to meet the increasing needs for biofuels and renewable materials. One study was conducted that successfully converted 30% of anhydroglucose units of cellulose into starch, which is a promising start. This idea is possible because of both cellulose and starches being derived from the glucose monomer. The differentiating factor between the two is the beta or alpha linkage. Cellulose contains the beta linkage, which is a straighter link than the alpha linkage found in starches. While starches can be digested by humans, cellulose cannot. Because cellulose is more structured, it exhibits better strength and doesn't break down as easily. Cellulose can also form microtubules that can better support the materials and aid in additional porosity. Both cellulose and starches are abundant in nature and formed by condensation reactions. These two simple structures could further enhance materials and their properties, as well as the polymerization of others. These materials are the smarter, cheaper, and more environmentally friendly route to ease the food, biofuel, and environment trilemma.